Hello, everyone. Hope you're doing well. Last week, we were talking about normed vector space, a special type of something that we've been talking about this whole class, which is the notion of a metric space. Normed vector spaces add a little bit more structure to distances in a space. For example, some distances are very strange and don't work very methodically. You would imagine that if you had a sequence of points that converge to a point in a discrete metric, that they would, if you got them closer and closer to each other, then they should go and their distances should be getting closer. You could imagine, for example, taking a sequence like 1 over n on a space like for the real numbers with the discrete metric. But the issue here is that our notion of closeness with 1 over n conflicts with what discrete metric thinks is close. For something to be close in the discrete metric, it has to be exactly equal to the point. So we talked about how the sequence 1 over n does not converge to 0 inside of the real numbers given the discrete metric, even though it absolutely does converge given the standard metric. And the reason is that the discrete metric has a notion of distance that is what I like to call, and I've said in office hours before, the fisheye lens. You imagine like you're looking through something and you have like whatever's right in front of you is right in the center of your lens, and everything else, even if it's really close, the concavity of the lens pushes it over here to the very rim of it. Any points that you have inside of the real numbers, every other point that is not equal to that point has a distance of exactly 1 away from that point. Even this picture is only so good at depicting that, as you would imagine diagonal elements would be of distance a little larger than 1, but this is true regardless of the dimension. So you can see if you're trying to picture this, you're looking at an infinite dimensional picture. Every point is at least 1, is going to be 1 point away, exactly 1 away from this point right here. It all comes to the edge of a circle. But norms have a little bit more niceness to them. Norms are continuous in a neat way, kind of like how discrete you have some sort of neat notions of continuity, but it adds a little bit more of that niceness to it. If you have a sequence converging in norm, then the norm itself is going to also converge to 0. To write that, if you have a normed vector space, if you have that x sub n converges to x with respect to the norm, then that's going to imply that the distance or the length of the vector x sub n minus x is converging to 0. You have this notion of continuity with the norm, which gives it a little bit of a well-defined notion of length inside of a space. So you're adding to the notion of distance, which is what you get inside of a metric space. You're adding to that the ability to define lengths of vectors inside of your space whenever you're looking at a normed vector space. We're, of course, also adding all of the typical axioms that we use when we define a vector space, namely that addition and scalar multiplication are well-defined operations on our space, where associativity, commutativity, and the distributive law work very nicely all with each other. So there's metric space, there's normed vector space, and the thing is that when we looked back at our 8-0 video lecture, we saw that Rn has a little bit more structure to it, because not only can you find distance between 2 points in Rn, not only can you find the length of any vector in Rn, you can also say that given 2 vectors inside of Rn, you can define angles. Many reasons we might want to do this. One, we talk about the triangle inequality all the time, but the triangle inequality looks like a triangle because it has angles in it. And that's the picture that we give when we are trying to define the triangle inequality for metric spaces, even though triangles have length. They also have angles with them, and metrics don't have those two things as being well defined. It's our best shot at being able to understand what's going on when we define the distance from x to z to be less than or equal to the distance from x to y plus the distance from y to z. So when we talk about the actual triangle inequality, in order to be able to define triangles on a space, we need a little bit more structure. That structure that we talked about in 8-0 comes from the dot product. And we will be generalizing that notion in this video lecture to talk about the inner product spaces. Now, inner product spaces are normed vector spaces, and we'll see why that is true. In particular, these things have to be vector spaces. So all inner product spaces are vector spaces. It will have all of those axioms. But we're also going to add a little bit more structure to it. Now, you might think about, as we go through the different parts of the definition here for an inner product, you might go ahead and put the dot product in your mind. And remember that there's two versions of this dot product, one of which works on the real numbers and one of which works on the complex numbers. And we'll be a little bit picky here depending on what kind of situation that we're in. I'll go ahead and introduce both, even though for most of this class, we're going to be sticking to the real numbers just for the sake of simplicity, because in some of the applications you may be seeing later on, you may need to be working in the complex numbers when it comes to looking at inner product spaces. In fact, when we start moving into inner product spaces, typically the complex numbers become just as viable a space to look at as the real numbers, whereas maybe in some of the other spaces, the real numbers are a little bit more commonly seen in applications. Here, complex numbers, they appear naturally. This is where we start getting to solutions of differential equations and finding those solutions or approximating them using things like Fourier series. And to find some of those solutions of differential equations, oftentimes we have to take a trip into the complex numbers to find our solutions. You may have seen values like e to the I theta before. If you have seen that, the big reason that it comes up so much in a complex variable course is that it is itself a solution to some differential equations. So that is a discussion for another day. For now, let's talk about what the dot product looks like in terms of the real and the complex numbers. And while I'm doing that, take a look here at the parts of the definition for the inner product and confirm for yourself that these definitions work as definitions of this more general thing called an inner product, which can be defined on any vector space, not just on Rn. So let's take an R vector space, which we know is something in which it is well defined for you to take something and multiply it by a scalar real number and still get a vector inside of the space. A canonical example of a real vector space is Rn. Then we define the dot product between two vectors to be equal to this. You take one of the two vectors that you're given here, I'll take y, and you take its transpose, and then you multiply it times the vector x. Another way that this is commonly written is that you can take the sum as I goes from 1 to n of the corresponding elements inside of each of the vectors, multiply those components, multiply together, and then add it as I goes from 1 to n over all of the possible dimensions you could be adding them in. An example is that the dot product from 1, 2, 3, 4 is equal to, you could take the 2 by 1 matrix 3, 4 and multiply it times the 2 by 1 vector, 1 by 2 matrix 3, 4, and the 2 by 1 matrix 1, 2, and just multiply those values together. You get 3 times 1 plus 4 times 2. This dot product is equal to 11. Now, a complex vector space, for example, we might be looking at something like Cn, in which we do this. Then the dot product in here is a little bit different. And you might see now why I actually put y here first instead of x. And that's since we're going to have to take the complex conjugate of elements inside of this vector. For example, if you have that this vector is 1 plus 2i and 3 plus 4i, then recall that the complex conjugate of a vector is taking the conjugate of each of its components, which means switching the sign of the imaginary part of each of the values within. 1 minus 2i and 3 minus 4i. We'll see in a little bit why we absolutely are very picky about y being the thing that gets the bar over here and why we need the bar in the first place. But now, for example, if I take this vector 1 plus 2y, and let's say I take its dot product with itself, just for the sake of clarification of what we're doing here, then what we're taking the product of is, if let's say that these are both x and y in this example, then we're going to be taking 1 minus 2i and 3 minus 4i. We're going to be multiplying it times the 2 by 1 matrix, 1 plus 2i, the original vector, and 3 plus 4i, and seeing what we end up getting from that. Well, we're just going to be multiplying these things together. We'll have 1 minus 2i and 1 plus 2i multiplied, plus 3 minus 4i and 3 plus 4i. Now, some of you have probably already seen this before, but I'll go ahead and show it again. If you multiply two complex conjugates together, what you get is called the norm of that vector squared. Let's see what I mean by that. If I multiply outer and inner here, I'm going to get things that cancel. This is a little bit like difference of squares, a minus b times a plus b. So what I end up getting is 1 squared minus 2i squared from multiplying this. Similarly here, I get 3 squared minus 4i squared. And if I take a look at this formula, the I squared is -1. So this actually just becomes 1 squared plus 2 squared. This just becomes 3 squared plus 4 squared after going through and putting all of this stuff together. Notice that this is the square of the distance of which we have been calling the modulus of this complex number. Same thing for 1 plus 2i or 1 minus 2i. Same thing for 3 plus 4i. These lengths are the square of the lengths of the values of the complex numbers themselves. So this number, for example, is 5 plus 25. This answer is 30 for these dot products. Note, it's a real number. In fact, we will see here that the dot product of every vector with itself has to be a real number. In fact, that's condition 1 here of the inner product. Although an inner product is allowed to be a complex number, and multiplying and doing a dot product with two different vectors may indeed yield some such a vector, what we see here is that whenever you take the dot product of a vector with itself, you have to get a real number. In fact, that real number has to be non-negative. And the only way that you can get the inner product of a vector with itself to be equal to 0 is if the vector itself is equal to 0. This might be familiar to you. This is something else that we require of a norm. If you have a non-zero vector, it has to have a non-zero length. Similarly, we are going to make a connection between inner products and norms by saying that you can induce a norm on a particular vector by taking the square root of the inner product of the vector with itself. To give some clarification as to why we do this, let's take a look back at what we had over here. Remember that we said that the length, or the modulus, of the vector 1 plus 2i is equal to the square root of 1 squared plus 2 squared, from going right up to above here. This looks a lot like how you would define the Euclidean norm on any given space. Same thing for Rn, by the way. I'm doing this in Cn, but this same sort of argument would work in Rn. So if I take the inner product of a vector with itself, I'm getting the notion of the length squared. So if I just want to find the length, I need to just square root both sides. That's the square root that we use in defining the norm of a vector x. This works not only in Rn or Cn, which are the examples that I'm using to motivate the different parts of the definition here, but will also work for any inner products that we define on any vector space. It will have to satisfy this condition 1 so that we can well define the notion of a norm, vector x, to be what we want it to be. Basically, this part of the definition is in there so that every inner product space is also a norm space. So anything we talked about last week is also true for this week. Any of the theorems, any of the definitions, anything that we learned about with norm vector spaces last week is also going to work for inner product spaces. We're specializing a little bit more, which, by the way, means that every metric space theorem that we have also works for inner product spaces. It's neat to be able to continue to add layers of structure and find more and more beautiful things to do. But let's keep talking a little bit about what we can do past that point. This second condition may explain why we have to take the conjugate of one of the vectors here. We already saw one reason why we need to take the conjugate. It's so that we can get difference of squares right here, so that we can get actual real numbers. Note that if I took 1 plus 2i and multiplied it times itself, I'm not going to get my imaginary components to cancel. I'm going to get that this one ends up being 5 plus 4i. And that's not going to work very well for the notion of a norm, which needs to be a real number each time that I define it. But given that the inner product is allowed to be a complex number, the question exists of what happens if I switch the two vectors inside of the space. Notice for Rn, if I switch the location of where 1, 2, and 3, 4 exist inside of this definition, then I'm not really changing much, because all I'm doing is switching where x sub I and y sub I are inside of each of the individual products. It's not changing much at all. In Rn, the inner product is known as symmetric. Symmetric meaning that if you take the vectors x, y, and switch them, you get the exact same inner product. This is a symmetric product here. All right. So that's what this is meaning. Now, the conjugate notion of this, we actually call this literally conjugate symmetric, is that you take the two vectors and you just switch them around, but you have to add a bar over them. Let's see how this works with respect to the dot product that we're given here. In fact, you might notice that this is actually one of the problems that we have on the slide underneath. We will talk about that one in just a little bit. But briefly, this should be because if I'm taking the bar of y transpose and I'm multiplying that times the vector x, just like I would two matrices, then I could think of this as I could also add a double bar to any one of my two vectors. I could add a double bar to the vector x. Because if I take the conjugate and then take the conjugate again, I'm back to the same vector. Now notice that I have an entire bar over my entire space. So something I can do here is I can just make that bar whatever I have for this remaining vector. This is the bar of the notion of y transpose, now without the bar, times the vector x, now with a bar. Finally, it doesn't matter in what order I put the transpose or how I order these y's and x. Now I have to, if I'm flipping the direction of y transpose and x, I also have to give one the transpose in order for the sizes of the matrices to work well in terms of their multiplication. But this is also equal. And finally, this is the definition of the conjugate of y, x. This being the definition of xy, we have shown exactly this condition 2 here. So the bar is needed so that we can be defining norms. And what that means is that if we're flipping the two vectors x and y, we end up getting a bar over the inner product. The last thing is that in the third condition is that the inner product, which we will sometimes write in this way to mean that the inner product has two arguments, the little dots tell you where you could put something in, that the inner product is linear in the first argument. That is, if you have alpha x plus beta y times inner product with the vector z, then you can break up sums and you can bring, say, scalars outside. You can break up sums, meaning you could write this as alpha x z plus beta y z. So scalars, so sums could be broken up here. This is totally allowed by condition 3. And what's more, you could take something like alpha x comma z, and you can bring the alpha outside to get alpha times the inner product of x comma z. Same thing, you could bring this beta outside for y comma z. You might ask, could I bring the alpha and beta outside? Could I do all of this if I'm looking in the second argument? Well, the thing is that we have to be careful with that. If you have something that is a sum or a scalar in the second argument of this, then you almost get this to be true. I have to change this a little bit to add some of the extra things that need to be considered in order for this to be true. And what that is that I have to be putting bars over certain things. Let's talk about why I put the bars here the way that I did. If I have something that I need to be breaking up scalars and sums-wise in order for this inner product to work, then I have to be using condition 2 to be able to basically make the second argument the first argument. And whenever I do that, I have to add a bar. So here, I'm adding the bar in the second expression because I'm flipping the two arguments where the linearity is what I'm testing in the second argument, so that this sum of scalar of this linear combination of vectors ends up being in the first argument of this inner product. At that point, I can use all the stuff that I would typically use for the first argument, but notice that the bar sticks around. Finally, if I switch x and y to be back to where they were before, then I lose the bar over y comma x, but I don't lose the bar over the scalars. If I have alpha and beta here, then the bars are going to stick around. So this is something called conjugate linear. Conjugate linear means this: if you have sums in the second argument, totally fine to split them up. No questions asked. But if you have scalars to bring outside the inner product, whenever your scalars are inside of your second argument and can be brought outside, then you're going to have to add a bar over them. Think back to our example with Cn. In our example with Cn, if we added, instead of looking at alpha and x dot y, we looked at x dot alpha y, then notice where the bar is. The bar is over the entire vector alpha times y. So the bar is going to go over the alpha and the y. Essentially, if I multiply the vector times alpha, then I have to multiply the entire dot product by the conjugate of alpha there. So that's something I wanted to kind of go through and show you a little bit, is that sometimes the complex numbers can add a little bit of extra structure that we don't typically see. But when we're looking at the real numbers, all of these things work very nicely. Notice that even if we're in the real numbers, the only thing we're asking in condition 1 is that the inner product of the vector with itself be greater than or equal to 0, with equality if and only if the vector is 0. Here, condition 2 also works very well because the inner product can only be real. In fact, we will say that the inner product on a real vector space can only be a real number. So if the vector space V is a real vector space, then we will say that the dot product must be something that goes from V cross V into the real numbers. The inner product must be real. So that tells us that if you have real numbers here, then you need to be able to take things that are just real numbers and multiply them in this way. If that's the case, then the conjugate of any real number is just going to be itself. Because if you take 5 plus 0i, which is a real number, and take its conjugate, you're going to get 5 minus 0i, which is still 5. You still get the exact same number that you had from when you started. And lastly, you get linearity in the first argument, and because you can flip the two arguments around willy-nilly, you actually get full linearity in the second argument as well. So we can define inner products for real or complex vector spaces. So now that we've explained the argument a little bit for this problem, let's see if we can do it now fully. Let's flesh out the argument. First, showing that the dot product is an inner product on C2. Now, just like norms, just like distances, you want your inner products to always be finite as well, because we asked for the inner product to always be a complex number, and infinity is not a number. So that's something else that we need to be careful of. So we'll do that as kind of like a rule 0. So here's a 0th rule, which is that we need for the inner product of a vector, the inner product of two vectors, to be finite. So we want to show that x, y, whatever it is going to be less than infinity. You'll see me use these bars a lot, especially when dealing with inner products on something like C2, because in order to say something is less than infinity, I can't compare complex numbers. I can't make one complex number greater than another, whereas I can do that with real numbers. And whenever I take a length or a norm, I get a real number. So now I can start comparing things against infinity. But in order to show that you get a complex number whenever you take an inner product of two vectors, it suffices to be able to say you can take its length and that its length is finite. So that's exactly what we'll do. First, note that the length of two vectors is the sum as I goes from 1 to n of x sub I times y sub I bar. That I just have to take a complex conjugate of each of the components of the vector y. If I can show that this is less than or equal to less than infinity in terms of this value, then I'm good to go. But this is a finite sum of, or is the square root of, I should say. This is the square root of a finite sum of finite products. And I think that's good enough for us. You're taking x sub I and multiplying times the bar of y sub I, and you're only adding finitely many of those products, which themselves give you finite numbers. So we should be good to go on the 0th row here. On 1, we want to show that when you multiply things out as we asked for in the definition of the inner product, that is, we want to show that the inner product of any vector with itself is going to be greater than or equal to 0. That formula looks like this. We're going to have the sum as I goes from 1 to n of x sub I times x sub I bar. But you may know this, and because we've talked about it already, is that the product of each of these things is just taking the sum of the magnitudes of each of these components, x sub I, and squaring it. We saw that example happen right over here. That all you have to do is take each of the components of the vectors that you get and then just add them together. Just take their lengths, square them, and then add them together. Well, this is absolutely greater than or equal to 0 because x sub I squared has to be greater than or equal to 0 for all I. It is the square of a non-negative number. So it is absolutely going to be this way. So it is less than or equal to 0 or greater than or equal to 0 for all I inside of the set going from 1 to n. So the square root of the sum of all of these non-negative numbers has to also be greater than or equal to 0. And it's also well-defined. I say well-defined because we're getting a is also real, I should say, maybe better to say, because we're not getting a negative number because of the square root. So this is something that is greater than or equal to 0. This works very nicely. That's exactly what we want for being able to take the inner product of a vector with itself. Now, what about the other part? What about the equality part of it? What's more, if you take the square root of the sum of I equals 1 to n of x of I, and take it, we'll just write it in this form, the length of each x of I and square it. It is actually a modulus, I should say that. If this is square root is equal to 0, then we want to show that the entire vector x is full of zeros. That's what it means to say that this vector x is equal to 0. You may have noticed that I bolded the 0 here and may have wondered why I did that. That's because I'm thinking of this not as the value 0, but saying that the vector x is the 0 vector. When I write 0 vector, I mean the vector full of zeros. The length of that 0 vector is whatever the dimension of our vector space is. So what's more, if this square root of sum of moduli of the x of I squared is equal to 0, then, well, we can just square both sides first and get something like this. This is also equal to 0. Well, how are you going to get the sum of non-negative numbers and get that to be equal to 0? It has to be the case that the sum of x of I squared is also equal to 0 for all I, which will imply that the x of I are also equal to 0 for all I, and hence x of I has to be equal to 0. You can't have a positive real or imaginary component for all I, which that will imply that the vector x is the 0 vector. Or we can just write 0 with a little hat on it like this. So this gets us the first rule for showing that this works. It's just saying that we can take the inner product of a vector with itself, get something greater than or equal to 0 with equality if and only if the vector itself is equal to 0. Notice that as we're doing this, we're actually talking a little bit about this second question here, which is, can we compare this induced norm to one that we have seen before? And the answer is yes. This is the Euclidean norm on Cn, the one that we defined as the standard norm on these spaces, which is the square root of the sum of the moduli squared. In this case of the real numbers, this is just taking the square root of the sum of the numbers themselves squared. We have to take moduli in order to be able to take a square root of a real number. Otherwise, we'd have to do some weird stuff with square roots of imaginary numbers, and we don't have to be in that business here. We've got two more conditions. One of the conditions we've already talked about, which is that you want to be able to show that you can take the inner product of two vectors and switch them at the cost of adding a bar to your inner product. Well, using the definition that we had from before of this being the bar of y transpose times the vector x, remember that the way we did this was we said that this is the same as adding a second bar or two bars to the vector x. This is the arrow. There we go. So this is the same as taking y transpose the vector x, having a bar and putting a bar over the entire thing because of this bar right over here. And then this is equal to taking the flip of these two vectors, keeping the bar over it. And this is the definition of y x bar. So this is what we get. All righty. So that gets us condition 2. And the last condition is that of linearity, that we can take something of alpha times the vector x plus beta times the vector y. And having that inner product with the vector z allows us to break up sums and take out scalars. Alpha times x, the inner product of x and z, plus beta times the inner product of y and z. This is what we want to show at each step. There we are. Okay, so with condition 3, we just need to show that we can break this up, and we'll just use the definition of the inner product to do so. We're going to be taking z transpose of alpha x plus beta y. And because vectors work so neatly, in fact, because matrices work so neatly, we can break up these sums and these scalars without much justification at all. If you're curious, what you could do to do this is just essentially break this up into the other formula that we have for this inner product, which is going to be taking each of these values and just breaking it up into, this is the sum of alpha x sub I plus beta y sub I times zi, and then adding each of those together. I goes from 1 to n. And then after this point, just break up using the fact that the sum is linear. You can take out an alpha if you break up all of the sums in the x sub I, z sub i's, and break up all of the sums into the y sub I, z sub i's, and then just bring out the alphas out of each of those and break them up very neatly. I'll go through briefly what that might look like. This would be the sum as I goes from 1 to n of alpha x sub I, z sub I, plus the sum as j goes from 1 to n of beta y sub j, z sub j bar. And this is something you can bring the scalar outside of. And once you are left with all of this, you're looking at alpha x z plus beta y z. So this answers our question and shows us what it means to show something is an inner product. These are each of the conditions for showing an inner product out of this space. Let's do it again. But this time, let's do it with something else. And while we're doing this the other example, we're going to be doing a very similar thing as to what we did in the previous example. So some of this stuff might look very familiar and will become a little bit more of a pattern. But while we're doing this, I want you to think, what does this mean about angles inside of a space that we can take and define an inner product on the space of continuous functions? Because we're saying angles exist whenever you have an inner product. And again, our most important understanding of what angle we want to be taking is that of the right angle of 90 degrees. We're going to be able to define something called an orthogonal basis of functions as we start moving forward through this week. So keep that in mind as we start taking a look at this next example. So here we are. Here's our problem. Now I'll go ahead and mention that there's going to be something a little strange to happen in the first condition. We're going to be using one of our homework problems. We'll look at homework 5, question 1, as a way to be able to work through and solve through one of these conditions up in here. So first, let's start with our zeroth condition. Zeroth condition is that can we show that this is actually a finite value? And what we're going to use for this, again, the inner product here is taking the integral of the product of the two functions, where the second one has a little complex bar over it. Again, if this were continuous functions going from the compact interval from a to b, going into the real numbers, we wouldn't need this bar at all. If it were going into the real numbers, the bar of any real number is real, so it would just be the product of the two functions, and then we just integrate those. But we know why that's probably there. It's probably in order for us to take some sort of norm later on. But first, let's go through and show that this is a inner product. So to start that, we need to make sure that this is actually a finite value. We know some integrals can be infinite, and we're looking at just any two continuous functions on the interval going from a to b. Well, since f and g are continuous on AB, so is FG bar. If you multiply two continuous functions, then you get a continuous function. If you take the complex conjugate of a continuous function, you still get something that's continuous. You can still write the function down without putting up your pencil. Maybe you have to flip it across the imaginary axis, but that's like saying you can take the negative of a function and get it to still be continuous. So we're looking at a function that is continuous on a compact interval. AB is compact. What that means is that the consequences of the extreme value theorem apply. But basically, we've said this before, that if you have a continuous function on a compact interval, it is bounded. That was from video lecture 7-1. So we have that max for x inside of AB of the value of f of x, g of x bar exists. Hence, the integral of f and g, this value right here, this is less than or equal to, this is less than or equal to, because we can just assume that we have the maximum value of this function and work through it like that. And also, I may need to be taking bars around in here because this could be a complex number. And in order for me to write less than or greater than, I need my numbers to be real. So I will have to say that whatever this is less than or equal to the max, as x goes from a to b, of the modulus of the value of f of x times g prime of x, or g bar of x. This value right here, the maximum possible modulus of this function here, times the length of the function. How long am I integrating for? Basically, the way to think of it is, in order to find the area underneath an integral, then the bound, the best possible bound that you can get for integrating something on this region going from A to B is if you take the largest possible value that you could have it be, and then look at the area of the rectangle that's underneath there. Then this integral has to be less than the area of that rectangle. So that's the picture that we have. And this is exactly the area of that rectangle. It's the maximum possible value of the function given right here times the length of that integral going from A to B. So this gives us a less than or equal to of something which is finite. And that's our 0th step. Basically, we've shown now that the inner product here has to be something that is finite. It's at least a complex number, so we're good to go. Now we can move on to our 3 different conditions. We need to check about what the inner product of a function f is with itself. Writing that definition down, we'll have f of x times f of x bar dx. And that integral, we have the product of a number, f of x, times the complex conjugate of that number. This is true for all x. So this becomes the integral from a to b of the absolute value of x, quantity squared, the modulus of f of x, quantity squared. What I'm doing there is I'm just ignoring the integral there and looking at what the numbers are inside of the integral. F of x times f of x bar is just like what we had back in our previous part. That's the sum of x of I times x of I bar. So I can replace it with the modulus squared of that number. Same thing here for this integral. Well, this is a integral of a non-negative function. The modulus of f of x is non-negative. I'm squaring it. That gives me something non-negative. So this has to be greater than or equal to 0. So I have something that's greater than or equal to 0. That's pretty good. So now I need to figure out what happens if the integral of a b of f of x squared is equal to 0. Is it true that f is equal to the 0 vector? What is the 0 vector for functions? That one might be a little bit tricky to figure out. Let's start there before we move in. For looking in Rn or Cn, the 0 vector is going to be just the list of zeros altogether in a vector. But what would be the 0 vector for functions? You may already have an image of what it looks like in your head. It's the function in which 0 everywhere, no matter what x value you plug in. We're going to call that the 0 function. So here, 0 is going to be a function for us where if you plug in x, you just get 0 for all x inside of whatever your space is. So that's what we mean when we say, is it true that f is equal to the 0 vector? The 0 vector is a function that if you plug in an x value, you get 0. It is the 0 function. So is it true that f is equal to 0? Let's see. If f is greater than 0 at some point, x inside of AB. So we are proceeding by contrapositive here by saying, let's say that we don't have that f is equal to the 0 vector, so that in fact, maybe f is greater than 0 at some point, or perhaps less than 0 at some point. If f is greater than 0 at some point, you may remember from homework 5 that if you have f is greater than or equal to 0 at some point, then actually f is going to be greater than some intermediate value at some point. Now I'm stretching what we did in our homework exercise a little bit, but imagine using the fact that f is a continuous function. What happens if you know the function is continuous at a point? Well, in order for it to be continuous, you have to be able to take a look at a little molehill. This has to be at some point, maybe it's at the peak, maybe it's on the way up, of some sort of function that you're looking at. So there's got to be some way that you're only looking at a part of the function where the function is greater than some non-negative value on that little interval. So basically the idea is, then if you have, looking at this point x, then there should be some way for you to take the integral of ab of the absolute value of f of x. In fact, we could square it if we wanted to. That wouldn't change too much here. That this is going to be greater than what happens if we take just maybe a little bit of a delta window around this function. Basically, we're cutting off little ends that are absolutely going to be either 0 or positive area to get this value right here. This is what we're doing here is we're attempting to capture this area right here, which very much seems to be in the picture a non-zero area. And that's because we know that the function is non-zero here, and so it has to be non-zero in an interval. And because f of x is actually greater than 0 here, and we can constrict the interval enough to all be greater than 0 inside of this interval, by our homework problem, we can actually get it to be greater than any value that's greater than 0. We could call it a. So this is going to be greater than a times the value of the distance inside of this value, because we can constrict it so that f of x squared is greater than a. So that's what we're getting. This is homework 5, question 1, that allows us to do this. So that means that if f is greater than 0, then this integral has to be greater than 0. So the contrapositive ends up being true. We haven't done this for f is less than 0, but you could imagine the same sort of principle happening. I'm just taking my picture and flipping it over the y-axis, the x-axis, excuse me. So similar if f is less than 0. So by contrapositive, if the integral of a to b of x, f of x is equal to 0, then it must be true that f is equal to the 0 function. Right? So that gives us condition 1. Told you this was kind of the weird part. It's got a little bit more oomph inside of it, and one of our homework problems ends up becoming useful. We can keep going now with each of these other components. 2 is going to look very similar to the previous example. And you might see why. We have to just take a bar over this entire function, which is going to move the bar from g of x to f of x. And it's okay if we flip the order of those two functions. Question 3 is going to say what happens if I take alpha f plus beta g and take its inner product with the function h? Well, that's going to be the integral of alpha f of x plus beta g of x times h of x bar dx. And what could we do with this? We can just now distribute inside of this integral here the bar of h of x to each of these components. And what's neat about the integral is that it is itself linear. If you have two terms that you're integrating over, you can just break up the integral between two terms inside of that sum. You could do this with any finite number of sums, in fact. So because the integral itself is linear, I can break up two sums, and I can even bring the scalars outside. And what I'm left with is exactly what I would be hoping to be left with inside of this problem. And in fact, so we're good. That gives us what we need. All right, so there we go. That gives us how we get this. Some of you may have been looking at this other question and trying to figure this one out as well. What is the induced norm of this inner product? What do I get when I look at this? It may be something that's a bit familiar to you if you remember going back to the video lectures from 8-1. This is the integral from a to b of the absolute value of x squared. And then, because we have to take a norm, we're square rooting that. This is known as the L2 norm on AB. So many of these norms that we've been looking at are actually examples of inner products, which is very neat. What we'll see in our homework is that there are some examples of normed vector spaces that do not become inner product spaces. In fact, taking a look at the examples we've looked at so far, we've been talking about the induced norm like the Euclidean norm. We've also called it D2. Sometimes we've called it little L2 and things like this. We've given it all these different names. That turns out to be a very special norm that you can get from an inner product. It turns out you can't get the norm D1. Recall that one being where you take the sum of just the absolute values of the components and you just add them all together. That ends up not being a norm or an inner product space. And that's what we'll talk about a little bit in our homework, that namely everything has to satisfy a particular type of law that we'll be discovering a little bit in over there. So inner products, very special and unique because they allow us to define angles between different operations. And what we've been seeing here is that sometimes those things you're defining angles for can look a little strange. We've just seen that you can now define angles between functions by looking at this notion of the integral. Now, I've been noticing this notion of angle come up a lot because that's how I'm understanding inner product spaces in total. But you might be asking, how am I actually finding the angle in between these two things? And the answer is the exact same formula that we would use back in the video lecture for 8-0, which is taking the cosine inverse of the inner product between the two functions divided by the lengths of those two functions. And where I'm finding the lengths of functions is I'm taking the inner product of each of those functions and taking their square root. So that's the formula for finding the angle. Now, the most important angle is the one we're going to be talking about now. Given an inner product space, we say that two vectors are orthogonal if the inner product between them is equal to 0. That ends up being really the angle that becomes useful to us. We can define and find angles between any two functions given an inner product on that space, but the real utility out of having an inner product space is being able to break things up into orthogonal bases. You may remember us doing this a bit when we were looking back through linear algebra, either in 632, 689, or back in your undergraduate context. And one of the things we talk about there is something called Gram-Schmidt orthogonalization. It's a way to break up a basis of your vector space into orthogonal components. And depending on the context that you had it in, you may have also seen where we define something called the orthogonal projection of a vector. In fact, orthogonal projections is exactly how Fourier series work. If you haven't gotten a chance to look at that, I know it's optional, but one of the videos that motivates this entire 5 weeks is video lecture 6-0, the one that motivates us based off of Fourier series. It motivates all the things that we're trying to do in these weeks that we're covering. So if you get some time, go back and take a look through those videos or that video and try that out. See what that's kind of looking toward, because essentially the way that you define a Fourier series is as a orthogonalization of a vector. So you need an orthogonal basis to do that, and you need a function that you could send through that. In order to do that, you need your function to be inside of an inner product space. And that's where we start getting these sorts of notions from. So let's talk a little bit about this notion of orthogonalization. First, orthogonal means exactly what you think it means in the context of Rn. Rn means that if you have two vectors like this, and if you take a look at those two vectors, u and v, then the triangle that gets formed by completing these things with a resultant vector, u plus v right here, that the angle that you get out of these, if this is a right angle, then this is a right triangle. A right triangle has a very nice formula for it, known as the Pythagorean theorem. It says that if you want to take the length of the hypotenuse, then you can find it. The formula for that is that the length of the hypotenuse squared is equal to the lengths of the corresponding vectors, the sides, the legs of this triangle added together. So the length of u plus v squared is equal to the length of u squared plus the length of v squared. That's exactly the formula for the Pythagorean law given right here. This is true as written in any inner product space. If you are given two orthogonal vectors in an inner product space, then you can write the exact same formula. If you have two vectors that make a right angle with each other, then this is exactly the case. Notice that this does not work if the two vectors are not orthogonal. If I have a vector u and a vector v right here, I don't know very much about the vector side that's given right here. I would actually have to use maybe like a law of cosines if I knew the angle between, maybe not the two vectors, this is actually this angle. Maybe I need to use like a law of sines or a law of cosines to be able to figure out what that length would be. So to find the length of things in orthogonal vectors, however, it's a very nice process. The length of u plus v quantity squared is the length of u squared plus the length of v squared. And that has a surprising amount of utility even in the world of functional vector spaces. So first, let's talk about this Pythagorean theorem, and let's try and prove it using only the definition of an inner product. None of our intuition about how Rn works or Cn works, but just using the definition that we had on slide 2 of our presentation here. Whenever I'm pausing the recording like this, I'm just trying to make a little bit more space so that I have enough space to look right around in to get to this problem. So let's do it. Let's prove the Pythagorean theorem. You remember, we are done if we get to show this equality right here using the fact that u and v are orthogonal. We'll typically use this symbol to signal this to be a signal of orthogonality. So this says u is orthogonal to v. Or in this context, to make the English make sense, let u, the vector u, be orthogonal to the vector v. So then we need to start on one side and try and get to the other. Well, here's what we're going to do. First, we're going to take a look at this value right here. This is the length, the norm of u plus v quantity squared. And we notice that we're using this in an inner product space to talk about norms, but the question is, don't we get this in a normed vector space? Because there's no real inner products anywhere over here. But we need to somehow use inner products because in order for vectors to be orthogonal, you need to be able to take the inner product between those two vectors. So maybe that gives us a hint about what we need to be doing. We need to break up this norm and make it look like it's an inner product. Well, we have a way to do that. The norm itself is the square root of the inner product of the vector with itself. So we're going to get something like this. This is the square root of the inner product of u plus v with itself, quantity squared because the norm is squared. The square and the square root gets to cancel out, so I have something like this. And now I'm taking a look at what I have here. I have two things being added here inside of this inner product. I have a u plus v in the first argument, a u plus v in the second argument. I'm going to now use condition 3 of our definition of an inner product to utilize linearity. And I'll do it here in the first argument because that's how that one is written. So here we have u and u plus v and u plus v. You may have noticed that I switched my notation there for the second argument. These two are synonymous with each other. Writing the vector u plus v is the same as writing the vector u plus the vector v. And that's my definition of an adding two vectors. Now, notice that we can actually do the same thing with our second condition because of what we talked about with conjugate linearity. So conjugate linear in argument 2. In argument 2. So because it's conjugate linear in argument 2, we can now break apart each of the two vectors we have now into smaller vectors. Now notice what we have. We have 4 vectors. Here's u and u. Here's u and v. When I break it up, these two vectors, I'm going to get v and u. Notice the order is important because we can't just switch these around if this is a complex vector space. Plus the inner product of v with v. This is 4 inner products all summed together. And notice that 2 of these are actually what we want. The thing on the left here, this inner product of u with itself, is the norm of u squared. This one on the very right, the inner product of v with itself, is the norm of v squared. Now, I'm going to do a little bit more explaining than I need to about these middle two terms because I'm going to actually use something about these two terms in a later component. But the inner product of u and v and the inner product of v and u, actually, we can already go ahead and say are 0. And how are we saying that they're 0? These two vectors are orthogonal, so their inner product is equal to 0. But I want to write something else. First, I want to write that these are can be rewritten to be almost exactly the same. V comma u can be written to have v u comma v at the cost of writing a bar over here. If this u comma v is a complex number as inner products are allowed to be, then this inner product right over here on the right-hand side is a minus bi. Notice that when I add those two things together, I still get a real number. This is the norm of u squared, the norm of v squared, plus this is 2 times the real part of the inner product with u and v. Here, re is a symbol for the real part of a complex number. The real part of a complex number, if this is a plus bi and a minus bi, then if this is the real number, if this is the number x, then the real part of x is a, and the imaginary part of x is b. Notice the imaginary number, the imaginary part is itself a real number. We're just taking the real and imaginary parts and breaking them apart. This is 2 times a. When I add these two numbers together, I get 2 times a. Now I can definitely say that this is 0 because taking a look at u comma v, that number is 0. The real part of it then is going to be 0, so all of this is going to be equal to 0. And take a look at what I started with, which was this, and take a look at what I ended with, which was this. And that gets us all the way through the Pythagorean law. Pretty neat stuff there. Tells us that we can go and break apart the norms of things whenever I have a right triangle. And again, this doesn't work for any triangle inside of our space. But we do have something else. Whenever you have a norm, and you have the norm of u and v added together, you still get that this is less than or equal to the norm of u plus the norm of v. And this is because what this is still a norm. So even if you have any two vectors, so this is for any vectors, then you still have the triangle inequality. That works for any triangle you can think inside of a space, whereas the Pythagorean law only works for right triangles here. So you still get things like the triangle inequality because what you're working with is still a norm, and the norm has the triangle inequality. This is an extra condition that tells us what we get to do with some of these inner products. Another thing that becomes very neat as we kind of look around and play with this is something called the Cauchy-Schwarz inequality. You may remember that's something we talked about back in the video lecture 8-0, and it may or may not have been something that you've seen before. The Cauchy-Schwarz inequality is a way to bound the inner product of two vectors. You may actually be familiar with the formula in terms of Rn, which says that the inner product is of two vectors is the norm of the two vectors multiplied times the cosine of the angle between them. This is the formula that's typically used to define the angle in Rn. But where this formula comes from is the law of cosines. And we play around a little bit here with the form to make sure that the inner product is the right thing to introduce into the law of cosines to get this formula to work. And it is. So this formula is a part, or it proves indirectly the Cauchy-Schwarz inequality for Rn. And the way that we know that is that cosine of theta itself in absolute value is less than or equal to 1. So if I take the absolute value of each of these components, then I know that this is going to be less than or equal to the norm of u times the norm of v. And that is the Cauchy-Schwarz inequality. That happens to work for any inner product space. If it helps at all, think that inner product spaces have nearly all of the intuition that we would have on a space like C to the n. Although we may not have less than or greater than on the two elements inside of an inner product space, we can do almost anything else. We can take their distances, we can take their lengths, we can take their angles. Much of the intuition that you would have in a normal space like C to the n, you have in an inner product space. However, you may not have completeness. And again, we talked about completeness and why it's important. Many proofs involve trying to take a sequence of numbers that get closer and closer to each other and to say that they themselves converge to a point. But you only get to do this if you can say Cauchy sequences converge, which only happens in a complete space. Inner product spaces don't have to be complete. We'll talk about that a bit in the next video lecture. But this theorem is saying that with just the structure that we have on the inner product space, the definitions of an inner product, that just with that structure, we have the same theorem that we would typically get from R to the n or C to the n. So let's talk a little bit about this theorem because it is so neat to get to talk about a bit. And this is going to be our first introduction to something called a projection. Projections are going to be the main talking point of vector spaces or inner product spaces for us. We are going to want to talk about vector projections all the time, because vector projections give us what we want whenever we're looking at an approximation of a specific value. Some of you may have gone through with computational linear algebra or another similar course and needed to compute maybe a least square solution. And you may have realized or been told that that vector that you're getting from a least square solution is the projection of your original vector onto a plane. That is a huge component as to why we study them in general, is that they give us good approximations of functions that live within inside a solution set that we want. Least square solutions are huge in computational world. So let's talk a little bit about some of these projections and how they help us with this Cauchy-Schwarz inequality. First, if I have the inner product here with a vector that is just a vector full of zeros or just the zero function, then I'm looking at here that is a norm of something that is like 0. Now, it may not be clear why the inner product here is going to be equal to 0. So let me go ahead and show you a neat thing. If I have the inner product of something like the 0 vector together with the vector v, then something that I can do to show that this is actually equal to 0 is this. Well, first, if I take a vector like 0 and I multiply it times 2, then that's still going to be 0. Or at least that's going to be something. We'll figure out what it is. we want to claim that it's equal to 0, but in our head, we automatically know that this function itself is going to be equal to 0. And in fact, that's true by the definition of the 0 vector, is that when you multiply the 0 vector times any number, you get something that's equal to 0. We know this from our, this is from our definition of the axioms of a real number. So if I take 2 times 0 times the vector v, I'm going to get something that's 0 times the comma the vector v in its inner product. But I can also use linearity, and I could bring out this 2. If I bring out that 2, then I'm also getting that this is equal to 2 times the inner product of 0 times the vector v. Notice that there is a chain of equality that takes us from one to the other. Well, if you have two numbers, one of which is 2 times the other side's number, and you happen to know that these two are equal, well, then by just subtracting 1 to the other side, you get that the inner product from 0 to v is equal to 0. A neat little fact there that says that whenever you have the 0 vector inner product with any other vector, that you get 0. So that's the this is clear component here that I typically don't like hearing or seeing, but I believe I may have gotten this from the text at some point. So I wanted to explain a little bit as to where that came from. So let's go ahead and say that the two vectors that we're working with now in this inner product are not equal to the 0 vector, so that the vector projections can be non-degenerate, that we can get some neat projections here. Let's take the vector p to be the vector projection of u onto v. So let's first talk a little bit about what vector projection is. You may remember these formulas, but I'll go ahead and write them one more time. That if you want to take the projection of the vector u onto the vector v, then that formula is this. You are taking the inner product of u and v and dividing it by the norm of the vector v squared, and then multiplying that times the vector v. So this is the formula for that projection. Essentially, where that comes from is that we are taking the inner product of u and v to basically get an angle between them. And if you kind of look at that a little bit, and you can start introducing a few terms and start getting a cosine in here, namely, I could take a look at this as the inner product with u and v times the inner product, or times the norm of u, and divide it times the norm of u times the norm of v. And then I can multiply that times the length of this unit vector in the direction of v. Well, this part right here, that's the angle. This is cosine of theta. That's the angle in between those two vectors. And what I have left over is the length of u and times the vector v in the direction of the vector v. And where that vector projection comes from is from this picture. If I have a vector like this and a vector like this, then the vector projection is to find the length of this vector that we would get right here. And where that comes from is the length of this vector comes from u times the cosine of the angle given between the two vectors that you're given. And if you would then try to figure out the direction of that vector, you're going to get a unit vector in the direction of your vector v. So this is the vector v in blue. The vector u is what I'm given here in red. And then what's here in purple is the vector, which is the projection of u onto v. So the length of this is going to be equal to the length of u times cosine of the angle theta, because of this picture that we have using some trigonometry there. And the direction is in the direction of v. In particular, in the direction of v, of a unit vector for v, because we don't want to be adding or subtracting length by multiplying it times this vector. So that gives us our formula for this projection. So that's where that sort of thing comes from. That may have been just a review for you, but basically where that comes from is that if you take the length of this vector, the length of this vector right here, then what you end up getting is something called the scalar projection of this value. Taking the inner product with u and v and just dividing it by one length of v gives you the length of the vector p, the vector projection. And that length of the vector projection is called the scalar projection. And that kind of summarizes point 2 of these facts. The first fact is the Pythagorean law. The Pythagorean law says that if you have a vector projection p, and you take a look at the original vector u that you start with, then you could subtract those two vectors. And as long as this is a vector projection, then this right here is a right angle. We'll go through and talk maybe a little bit more about that in a future proof. But this is going to say that these two things are going to be at a right angle to each other. From Rn, it's a little bit clear as to why that might be. For example, if you have the vector 1, 2, and you want to project it onto the x-axis, then you're going to be looking at a vector that has no y component because it has to be on the x-axis. And then subtracting those two vectors, you're going to get just the vector 0, 2. And the dot product between these two vectors would be 0. So because the vectors p and u minus p are both orthogonal to each other, we get to can move on with these two facts in tow to work and show the Cauchy-Schwarz inequality. Now, the reason I go through and introduce the projection here is so that we can make this proof pretty nice. Let's see it. Now that we've gotten the proof, we can start combining these two facts a little bit together, which is that the scalar projection squared, which is the norm of the projection p squared, is equal to, by using scalar projection, and the second one is by using the Pythagorean theorem. Then we can combine these two notions together to get that the length of the projection p squared is equal to the length of u squared minus the length of u minus p quantity squared. If we now go ahead and try and separate out to get a length just in terms of the inner product of u and v, we're going to get the inner product of u and v quantity squared, and multiplying across by this denominator of norm of v squared, we're going to get what we're looking for, which is, recall what we're looking for is the absolute value of the inner product for u and v is less than or equal to the norm of u squared, or norm of u times the norm of v. And we're going to get that minus something. That minus something is something that is minus a non-negative number, so we can ignore it if we'd like at the cost of a less than or equal to sign. Taking this left-hand side and this right-hand side, we notice that we get something very similar to this inequality here, just with squares on the left and the right-hand side. So we can just take square roots of both sides to get us the value that we would like. This was a neat one. I believe I got this one from the text, and let me tell you, I have seen proofs of Cauchy-Schwarz that make you want to cry a little bit. So this is actually neat to see it all condensed in this way, using some of the intuition that we have from linear algebra for vector and scalar projections. All right. Now, the reason that we talk about Cauchy-Schwarz inequality at all is to solve a problem like this, which is to show that the norm that you get actually does define a norm here. And what I'm going to do is, it's because we've kind of done a little bit of kind of checking all of the boxes here with this stuff. I'm just going to pause the video for a bit and actually show you what this problem becomes. So here is that proof. This is, again, showing that the norm of x that we've been talking about as a norm is what we call the induced norm. Now we can actually prove it. Notice that the third bullet point here uses this little inequality. And let me kind of give you a chance to look through some of this other parts here. But that inequality is what we've just been using, this Cauchy-Schwarz from the previous slide, which is why we needed to prove that before getting to this problem. First, inner products are finite, so the norm has to be finite. Whatever we get, it has to be a finite value. In fact, it has to be a finite real value. And also, the norm of each vector is greater than or equal to 0, since the inner product of x with x is greater than or equal to 0. And if the norm is 0, then we end up getting to a point where we see that the inner product of the vector with itself has to be 0. And we know by the definition of inner product, that means that the vector itself has to be equal to 0. The second condition of showing that something is a norm is that scalars can come outside at the cost of perhaps adding an absolute value to the scalar. So the norm of alpha times the vector x is, by definition of what that norm is, you put an alpha x inside of each of the arguments of the inner product. That's what it means to take the norm of a vector, the inner product of that vector with itself, and then square root it. We can take both alphas out. The one on the left gets out for free. The one on the right gets a bar. So we get alpha times alpha bar, or alpha times alpha conjugate, times the inner product of the vector x with itself. Well, that can be simplified. Any number times its conjugate is going to be the magnitude of that value squared times the inner product of x with x. That magnitude of alpha can come outside, and we're left with something that is equal to the norm of the vector x. So looking at what we had to begin and what we had to end with, that gives us this condition 2, that we can bring scalars outside the norm. The last condition is a little interesting as it utilizes this Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality starts with, I'm going to start with something that's of the norm of x plus y quantity squared, and you'll see why the squared is there in just a little bit. Well, one of the big reasons is that if I have the norm squared, I can just write the inner product of x plus y with itself here. So that's what I'll do. Then I'll use some linearity with this first argument, but only the first argument, to show that I can break this up, kind of like what I did with the Pythagorean theorem, to be the vector x inner product with x plus y, and plus the vector y with the inner product of x plus y. I'll zoom in here so that you can see what I'm writing on this next part. For each of those inner products that I have, I am now going to break it apart. The way I'm going to break it apart is I'm going to utilize Cauchy-Schwarz right here. Cauchy-Schwarz says if you have an inner product, you can make it less than or equal to the product of the norms of the two vectors that you get. The norm of the vector x times the norm of the vector x plus y. Now, typically, if we want to do things with angles, we put a cosine of theta here or something like this. But I don't want that. I just want to show the triangle inequality with this last part. And less than or equal to seems like I'm going in the right direction. What I would like to show is that the norm of x plus y is less than or equal to the norm of x plus the norm of y. So maybe you can see here why the inequality for Cauchy-Schwarz helps me. If I break apart this first inequality, I get the norm of x times the norm of x plus y. And if I break apart this second thing that I have here, the second inner product, I have the norm of inner product of y with x plus y is going to be less than or equal to the norm of y times the norm of x plus y. Putting all of that together, I notice that I have two common factors that I could bring outside of these parentheses, and that's the norm of x plus y. And what I'm left with is the sum of the norm of x plus the norm of y. At that point, I'm actually done. I started with, to begin with, the norm of x plus y quantity squared. And when I ended all this inequality business, I have a copy of the norm of x plus y on the right-hand side. So the last thing I can do is just divide through by that extra copy of the norm of x plus y and take a look at what I'm left with. The norm of x plus y is less than or equal to the norm of x plus the norm of y. And that gives me the triangle inequality, which I need to define a norm on an inner product space. So that clarifies and proves what we've been talking about, which is that inner product spaces are norm vector spaces, what are themselves metric spaces. We have what we talked about from the very beginning, that our circles are kind of concentric. There's a smallest circle in the middle and a biggest circle in the outer side. So now we know where inner product spaces lie. They are things with metrics. They are things with lengths. They are things with angles. All of these three things now get to be utilized hand in hand. If we know something that's true from norm spaces, it's also true for inner product spaces. If we know something is true from metric spaces, we also know it's true for inner product spaces. We cannot underscore this fact because we could go through all of the different theorems that we've been doing in chapters 3 and 4 and then repeat them for chapter 5 when it comes to inner product spaces. But we don't need to, because we know inner product spaces are those other spaces. So everything from chapters 3 and 4 apply in this type of space. We, in fact, get to add a little bit more structure and talk about what really distinguishes inner product spaces from the rest. And it's the notion of vectors being orthogonal. Having projections of vectors as well ends up being very important. This may not be a new definition to you, at least in terms of Rn or Cn or something like this. But we will say that a set of vectors in an inner product space is orthonormal if each individual vector has a norm of 1, and if each pair of vectors is orthogonal to each other. An example of orthogonal vectors might be like, or orthonormal vectors might be 1, 0, 0, 0, 1, 0, and 0, 0, 1 inside of R3. This is an orthonormal set. A non-example, so this is an example. A non-example is something like 1, 0, 0, 0, 1, 0. And then maybe we go 0, something like 0, 0, 2. This is a non-example, as we have a vector here that has a norm of 2. If I take the dot product of this vector with itself and then square root that, I'm going to get a length of 2 for this vector. So that is something that is not an orthonormal set of vectors. Another non-example might be, I might take two vectors like 1, 0, 0. I might do something like square root of 2 over 2, square root of 2 over 2, and 0. And then I might do something like just 0, 0, and 1. And this is another non-example because I have two vectors whose dot product is non-zero with each other, even though each individual vector has a length of 1. But just because I'm excluding these as non-examples doesn't mean that this is the only example of an orthonormal basis in R3. I could have gone and done some pretty interesting things to make all of that work. I could have done something like this: square root of 2 over 2, negative square root of 2 over 2, 0. And then I could have done, let's say, square root of 2 over 2. I have to kind of put this up in my head while I'm thinking about it. Square root of 2 over 2, then I could do something like, what does that give me? Negative 1/2. I have to think about it for a little bit. But one way to think about this actually and make some of these things work is that you can make something like the spaces of vectors that we've been looking at before. You can make these vectors orthogonal vectors. As like, for example, 1, 0, 0, 1, 1, 0, and 1, 1, 1. This can be made to be an orthonormal set using Gram-Schmidt orthogonalization. And what happens is sometimes you will get the standard basis that we typically see in R3, but it is not the only orthonormal standard basis. Maybe it's a little easier to imagine it geometrically. Geometrically, in R3, the three vectors that I am showing here are unit vectors in the x, y, and z directions. But I could take those three vectors, and instead of having them go in the direction of the axes, I could tilt them a little bit. Maybe I change the y vector to be going down this direction, and the z vector to be going this direction. Now, with this picture, I'm still going to have right angles everywhere. For example, if this vector is 1, 0, 0, this vector might be something like 0 square root of 2 over 2, and then negative square root of 2 over 2. And then this vector over here being 0, this one's going to be, I have to do this in my head again, square root of 2 over 2 over 2, and just positive square root of 2 over 2. Then these three vectors form an orthonormal basis. No, I haven't used the word basis yet. I'll use that next video lecture. But an orthonormal set inside of R3. These three vectors are all orthonormal to each other because they're all orthogonal, and each of them also has a length of 1. So it's very possible for you to be looking at different sets of orthonormal bases here. I didn't just have to do it with this rotation. I could have done it with any of the three rotations here. But the goal is with orthonormal sets for you to essentially be able to standardize your notion of how you are spanning different subsets of your space. Here's an example of an orthonormal set inside the space of continuous functions from negative pi to pi. And here's an inner product that we haven't seen before. Here's our problem. Let's show that the set given here is orthonormal in the space of continuous functions going from negative pi to pi with the inner products given by the inner product of f comma g equals. You notice that the integral part is familiar. The integral from negative pi to pi of f of x times g of x dx is in there and is rightfully in there. But it's also divided by pi. This is because, as we'll see, this makes our orthonormal set a little bit nicer to work with. It is definitely possible to find an orthonormal set without this 1 over pi in here for this space, continuous functions from negative pi to pi. However, then you have to be doing some extra stuff to your functions that you may not want to do. For example, if I take out this 1 over pi, it turns out that you can divide each of these entries inside of the set by a constant, and that constant ends up being the square root of pi, in order to let this maintain this being an orthonormal set. But I don't want my functions to have divided by square root of pi in them. I'd rather have a cost of my inner product having a 1 over pi in it. And that's the choice that we typically make whenever we're working with functions like this. In fact, these functions may look familiar to you if you went back to that video lecture 6-0. This is the set of functions that you use to approximate whenever you're defining the Fourier series of a function. Let's talk a little bit about why we use it. Well, one is that this is an orthonormal set. And orthonormal sets are very good at finding projections for them, as we'll see in some of the future slides in this PowerPoint. So first, let me get this one set up so that we can talk a little bit about what this looks like, how to show that this set is orthonormal. The first thing that we could do is start at looking at each of the individual functions and taking their inner products with themselves. To show something is orthonormal, you need to show two things. One thing is that if you take a vector and look at its inner product with itself, that inner product needs to be 1. With technically, the square root of the inner product of that vector with itself needs to be 1, but we don't need the square root because squaring both sides gives you 1. So that's the first thing that you need. The second thing that you're going to need is that you need to be able to say if you have two vectors that are non-equal, so u and is not equal to vector v, then that needs to imply that the inner product between those two vectors is 0. You may notice that there's an infinite number of vectors inside of this set. And that's actually possible here. Notice for R3, you can only get 3 possible vectors to be in an orthonormal set with each other because the number of things inside of an orthonormal set is limited by the dimensions of your space. However, the space of continuous functions is infinite dimensional. You have as many dimensions as you would like inside of that space. So that means that we could be looking at orthonormal sets that are infinite now in this world. And this ends up being one of the most useful infinite bases that you could have out there. I'm not going to be proving here that it's a basis, but it actually ends up being a basis for this space of continuous functions, if you allow for the Schauder component of it. That is, that you can basically get infinite sums of these things. And the fact that this is a Schauder basis is exactly why the Fourier series is something that is investigated and explored, especially in this in the context of continuous functions. But to begin to show that something is an orthonormal basis, we have to first show that it's orthonormal. So let's take the length of each of these vectors and try and take their inner product using this formula. If we take the inner product of the function, which is the unit function, 1 over square root of 2, the function that's just at this value the whole time, then that's going to be equal to, we're going to have 1 over pi because of the special inner product, times the integral from negative pi to pi of the functions being multiplied together. Well, if I multiply 1 over square root of 2 by itself, I'm just going to get the function 1/2. And I can bring the 1/2 outside. Once I bring the 1/2 outside, I can then just integrate x going from negative pi to pi, and that's going to give me 1 over pi times 2 times, this ends up being 2 pi. Those cancel out to give me 1. Maybe that can tell you a little bit about why I want the 1 over pi inside of this integral. It's so that when I integrate 1 over square root of 2, I get something that's equal to 1. And I can continue this process for each of my other pairs that I've got over here. I did a lot. Oh, I know why. Give me a second here. Needing a little bit of extra space there so that I can also show this for some of the other inner products that we're going to have. One of which is going to be taking the integral of sine of nx with sine of nx. Now, first, let me note that n is going to be just a natural number. So this could have easily been replaced with sine of x and cosine of x, sine of 2x, sine of 2x, sine of 3x, sine of 3x, each of the different pairs. But I can actually do them all at once. And the way that I'm able to do them all at once is by using a formula that we have from integrating trigonometric functions that's typically used maybe in a Calc 1 or a Calc 2 context. Some of you may be familiar with this and may be excited for the fact that some of this becomes useful later on, which is the fact that you're going to be integrating sine squared of nx dx here. And if you're going to integrate something like sine squared, you're going to want to use a double angle formula. Sometimes when it's written in this way, it is called a power reducing formula. This is going to be the integral from negative pi to pi of, in order to reduce the power of sine squared, something I can replace it with is 1 minus cosine of 2 times the angle that I'm integrating over, times divided by the value of 2 dx. So that's using something called a power reducing formula. So this is power reducing. And now I can integrate each of these things. It turns out integrating cosine 2nx over 2 is going to give me 0 over exactly these bounds going from negative pi to pi. Think when I integrate cosine, I'm going to get sine, and evaluating sine at negative pi and pi gives me exactly the same value. I'm making a full rotation around. This ends up just being equal to the integral from 1 over pi of the negative pi to pi of the remaining value, which is 1/2. And we just evaluated that one over here. We know that that's equal to 1. Similarly, cosine nx, if I take its inner product with cosine nx, then that's going to be equal to, well, the exact same thing. I'm going to have 1 over pi times the integral from negative pi to pi. Using a power reduction formula on what is now cosine squared of nx, I can replace that with 1 plus cosine of 2nx divided by 2 dx. And once again, integrating this cosine is going to give me sine, so that's not going to change much about the value that I get out of this integral. This is still going to give me 1. And that's it for the first condition. The first condition is that the length of each of the vectors that I have inside of my set needs to be 1. And that's exactly the case for 1 over square root of 2, the sine of nx's, and the cosine of nx's. Notice that I'm only integrating with respect to x because, again, n is something that I could just replace with any number here. Sine of x, sine of 2x, sine of 3x, cosine of 4x. All of those could just be replaced with any value, but I can actually show that each of them equals 1 when you replace any value in there for n. Then I can go through and show that the inner product of any two values of non-equal functions here is equal to 0, like 1 over square root of 2 and sine of nx, for example. And where that comes from is that if I take the integral now, going from negative pi to pi of 1 over square root of 2 times sine of nx dx, then I'm going to get a similar thing as to why I knew that this term was going to integrate to be 0 on both of these components. And that's because if I integrate sine, I'm going to get negative cosine. And if I get negative cosine and evaluate it at negative pi and pi, that's the exact same value. So this ends up being 0. Same thing for 1 over square root of 2 times cosine of nx as well. So anything compared with the 1 over square root of 2 is going to be 0 because what I end up getting from that integral is another trigonometric function of like sine and cosine. And it's because I'm integrating going from negative pi to pi, I'm still going to get 0. Then I could go through and show that, say, if you have sine of nx and cosine of m times x, where here n does not have to be equal to m, but it could be. To show that this is equal to 0, you are going to be using, this one might be a real call blast from the past, maybe from having to read about it at some point, but you may remember sum to product, or sometimes called product to sum formulas, using trigonometric formulas, which say that you can turn something that's like sine of something times cosine of something else and turn it into a sum of either sine or cosine functions in order to get that to work. I don't actually recall which one is which, but I'll go ahead and give a good old guess here that this is 1 over 2 times sine of n plus m times x divided by 2 plus sine of n minus m times x over 2 dx. And it may not be exactly this. It may have a minus somewhere, it may have a plus somewhere. Either way, you might notice it does not impact the value of this integral. You're still integrating sine or cosine on some of these values. And so it's very possible that you just get 0 for each of these. Notice even if n is equal to m, this sine of n minus m is still going to be sine of 0x. So you get sine of 0, and sine of 0 is 0. So this ends up still being equal to the 0 integral, even when n and m are equal to each other. The same thing can be done with sine of nx and sine of mx, cosine of nx and cosine of nx. All of the different combinations that you could be doing, it's going to be equal to 0. So I'm just going to write 3 dots and put a little smiley face and say that we are done. So using some of these different formulas, I've shown you a little bit about where each of these come from, either power reducing formulas or using this one here. This was sum to product, or product to sum, maybe more appropriate to say here. Using these formulas, we end up getting some very nice, neat integrals for what these values are. These integrals are all equal to 0. This is an example of an orthonormal basis on a space of continuous functions. And that's very powerful, as we are about to see, as we start moving into how we can use those things to define orthogonal projections. Now, reminding ourselves what we mean by orthogonal projections, I'll go back to Rn for just a little bit. Rn is a space that is full of projections. If I have a vector, like the vector 1, 2, 3, 1, 2, 3, if I have a vector like this, and I take a look at its projection onto the xy plane, which is something I need to do a lot in Calculus 3, is looking at projections of different shapes and figures into xy projections, something like this. Then what I'm doing is I'm looking at what I'm considering to be, I'll call it the shadow of that vector if I'm looking straight down the barrel of the z-axis, then that shadow of that vector will be 1, 2, 0. That is the projection of the vector 1, 2, 3 onto the xy plane. Another way I could have written that is that I could take the projection onto the space of vectors that is spanned by the xy plane. Here, 1, 0, 0 is the unit vector in the x direction, 0, 1, 0, the unit vector in the positive y direction. And I can take the projection of the vector 1, 2, 3, and consider what that projection looks like when looking straight down the barrel of the z-axis, essentially removing the z-axis component from any of it. The resulting vector that I get is ensured to be within the span of the vectors that I'm given right here. For example, the vector that I get, 1, 2, 0, is a linear combination of these two vectors. It is 1 times the vector 1, 0, 0, and 2 times the vector 0, 1, 0. So it is going to be the span of these vectors. So the projection of that vector u could be found even if we're looking at a plane that's not the xy plane, and even if when we're in a vector space that's not just Rn. But the way that you find that formula is very similar to how you might consider finding it in Rn. The formula for projections is given like this. If I am given an orthonormal set of vectors, for here particularly, I need my vectors u1 and un to be orthonormal for this formula to work. So we're working off of the basis of what we've just already done. Then if I want to find the projection of a vector u onto the span of the vectors that I'm given here. So for example, if I want to find the projection of 1, 2, 3 onto the span of the vectors 1, 0, 0 and 0, 1, 0, then something that I could do is start looking at the components of the vector that I'm plugging in the directions of the vectors that I want, that I use to span my given subspace, the subspace where I want to be projecting my vectors onto. So that formula could look like this. I could take the vector 1, 2, 3, and I can take its dot product with the vector 1, 0, 0. Taking that dot product, that is the component of this vector 1, 2, 3 in the x direction. So that's how much I want this vector to be going in the x direction. Then I can repeat that process for the y direction and give it that exact same scalar value. That scalar value is, I'm looking at the vector 1, 2, 3 and figuring out how much does it go off in the y direction. And to figure out how much it goes off in the y direction, I merely need to take its dot product to get to that point. Think of these as like scalar projections. Scalar projections were dot products over lengths of the vectors we're projecting on. And since we're in an orthonormal set of vectors, that length of this vector is always 1. So I'm always dividing these values by 1. These are scalar projections multiplied times the vectors we're projecting on. So this is the formula for adding together vector projections. Putting all of these together gives us exactly the formula that we had from before, that you can take 1 times the first vector, that unit vector in the x direction, plus 2 times the second vector, the unit vector in the y direction. This is the exact same formula that's utilized for Gram-Schmidt orthogonalization to end up getting you a good projection out of all of that. So this value, which we call capital P of a given vector, is called the projection of a vector onto a span. And again, we're using that notation of span to mean the set of all linear combinations of a given set of vectors that's given to us. For example, E1, E2, and so on and so forth is an orthonormal sequence in a vector space V. Then for every vector inside of V, the projection of that vector, which is the formula that we've just been talking about, this one right here, then this is an element inside of the span. It is itself a linear combination of the vectors E sub I that I'm using. In general, that is the inner product of the vector that I'm given, the one in green, like right in here, dot product with the basis vectors, no, not basis, but the orthonormal vectors that I'm using to span my space, times the vectors themselves, the orthonormal vectors themselves. Adding together all these projections gives us the projection of this element onto the subspace, which is the span of these orthonormal vectors. This vector P is something that's inside of the span, and I can actually make two claims about it. That this one is the closest vector to U that is inside of this vector space V. Another way to think of it is taking a look back here at our picture. If I consider the space of all possible vectors that exist inside of the xy plane, the only one that's going to be closest to the one where this length, the distance from the vector that is our projection, P of 1, 2, 3, the closest thing to the original vector 1, 2, 3 is that projection. The blue vector that we found is the one that is closest, meaning that the distance between green and blue is the smallest it possibly can be. This vector itself is u minus p of u. In fact, this vector is orthogonal to all vectors inside of the span of E1 through En. That was a little fact that we talked about before and used in the proof of the Cauchy-Schwarz inequality. However, we used it there because I wanted to first define the norm and show that inner product spaces are norm spaces. We aren't actually going to use that fact that the double bars is a norm in what is to come. So it's okay for us to kind of do things a little out of order, at least in the logic of what we're kind of proceeding through. So this is our proposition and one of our final ones to talk a little bit about. And since we're running out of time here for this particular video lecture, I'm going to just highlight some of the things that I think are the most important parts of what this proof is. First, knowing that we have a projection that is the closest possible point to this other vector is exactly what gives us least square solutions. If you have gone through the process of linear programming or just least squares regression, or something like this, then this is something that typically comes up in many applications later on for mathematics. This is a huge deal for most applications where you're needing to find a function that's close by. If you want to see one of these projections, take a look back at the video lecture 6-0, where I used the space of Fourier series that we were just talking about, the sine of nx's, the cosine of nx's, together with 1 over square root of 2, to find projections of a function and show you what I mean when I say that these things get close, that in distance, they're very close to each other. So that is the main idea behind what it is that we're doing. But we need to be able to do this with any given inner product space. So we just are using the definition of an inner product and that of a projection, that formula that we've been using in what is to come. Again, that formula for a projection of a vector, like a projection of a vector u onto a space of vectors. And typically the way that we would write that is we would have vectors E1 through En as this, and the vector u right here, then that is the inner product of u with E1 times the vector E1, the inner product of u with the vector E2 times the vector E2, dot product, or rather added to all of the possible other orthonormal projections that you might get. Each of these is on its own an individual vector projection. Using that formula for vector projections that we had from before, which is that you can take u, E1, take its, divide it by E1 in a product with E1 times the vector E1. The only difference with that formula of projection that we had for a vector u onto the vector E1 is that this inner product down here is equal to 1, because the vectors that we have are themselves orthonormal functions. So this is itself a vector projection, what we have right here. This is just adding up all of the possible vector projections we could get onto each of the individual vectors that span this space. So let's show that this works very neatly here. We'll first prove that you have that the vector u minus the projection is orthogonal to each of the individuals e sub I. If we do this, then basically all of these values for these inner products, u minus p of u, comma e sub I, are going to be equal to 0. And if that's the case, then we can bring the alpha sub i's inside. We can bring the sum inside of this inner product. And what we get is that for this thing, which is all linear combinations of the e sub I, which is, by the way, equal to the span of the E1 through the En, that this vector u minus p of u is orthogonal to every single vector inside of this span, because here the alpha sub i's could be anything, and you could be summing these, in any which way. So that tells us that you could take the inner product of any vector inside of this linear combination and show that it is orthogonal to u minus p of u. So that will say that this essentially, this vector that we're finding, if you take the vector u and consider its projection onto a given subspace, say it's this one right here, then the difference between those two things, this is going to be u minus p of u, that this vector right here is going to be at a right angle to everything inside of that span. And the only thing we need to do that is to show that it is orthogonal to each of the orthonormal vectors that span this space right down here. So let's see that. So let's note that if you take the inner product of the projection of u with e sub I, then what you get is, well, that's just by expanding this p of u. Remember that that formula is given right here. It can also be written as the sum as you add together each of the little indices of the possible terms that are the orthonormal vectors that span this subspace. You take the inner products of u with e sub j and multiply it times the vector e sub j. Now, that's true, and you can take this sum outside, and you can take these scalars outside, and all that you're left with, vector-wise, inside of this inner product is e sub j and e sub I. Now, notice that these inner products are very interesting because these are the inner products of two vectors in this orthonormal set. E sub j and e sub I, these two are orthonormal vectors. And if they're not equal, then their inner product has to be 0. The only time that these two inner products would be non-zero is whenever you're looking at the same vector, when e sub I and e sub j are actually the same thing, in which case it would equal 1. So this sum devolves very quickly. That is, that if you look at what actually ends up happening, that you get a lot of 0 terms in this, and all that you're left with is that the projection of u onto e sub I is equal to the inner product of the original vector u times whenever j is equal to I, e sub I for that vector. So if we now look at taking the inner product of u minus p sub u on the vector e sub I, we can use linearity, break that up a little bit, and get essentially that these two things end up being the same. You're subtracting the same thing from itself. That's going to end up being 0 for this inner product. Essentially, this is the picture that goes along with that sort of proof. But that also works in terms of functional vector spaces and any other sort of space that we might have. We get right angles between those vectors. And we saw that that was very useful in proving Cauchy-Schwarz inequality in our previous slide. Now we're going to show the other part of this, that p of u is actually the closest in the span to the vector u. So let's take w to be another vector inside of this span. So basically, now we're going to do this picture. We've got our vector, which is our projection. Here is the projection of the vector u given as this. So here is u. And let's say that you have another vector, and that is some other sort of vector inside of the span. We want to show that this distance right here is longer than this distance right here. From the picture that I've drawn, that's very obvious, but how could you show that any other vector that's given inside of this space? So we want to show that this distance is longer than this distance. This distance, we want it to be shorter, because this distance is that of u minus p of u. So let's do that. To do that, we will need to show that the difference between these vectors here, if we call this vector w, then we want to say that this distance u minus w is greater than the distance of u minus p of u. Well, we've just shown that u minus p of u is orthogonal to any vector in the span, and that includes, by the way, this vector right here. If you take two vectors inside of a space and you take their difference, this vector right here is also going to be inside of the space. So I'm taking those to the difference between these, p of u minus w, and that's the difference of two vectors inside of the span. So the way that we're going to do this is by using the Pythagorean theorem. Pythagorean theorem, how does it come in? The vector u minus p of u is orthogonal to any vector inside of the span. That is, u minus p of u is going to be orthogonal to the vector p of u minus w. This vector right here that I've just drawn, this one, this is p of u minus w. This is orthogonal to the vector given here, u minus p of u. These two are at another right angle with each other. Now, that's going to come in just a little bit. But notice that if you take the difference of these two vectors, what you get is u minus w. Now, make sure I'm kind of getting that right. Or rather, if you add these two vectors together, that's what I should have said. If you add these two vectors together, then what you get is the vector u minus w. So we'll start with taking a look at the length of u minus w squared. That's something that I know I want to use as part of my inequality. Well, by breaking apart u minus w, adding and subtracting this p of u in there, that is to get to this point right here and utilize this orthogonality, I can just say, okay, I can replace u minus w on the inside of this norm by adding and subtracting this p of u inside of this norm. But this is a vector, I guess we've been using u in this proof, so maybe we can call this a vector x plus a vector y norm squared. So Pythagorean theorem, that guy's coming back now. Pythagorean theorem says I can break this up into the norm of x squared plus the norm of y squared. Well, the norm of x squared is the norm of u minus p of u quantity squared. And then I get this little extra part that I actually don't need. Whatever this value is, it's too big. It's something that I could get rid of entirely and just say that this is greater than the thing that I wanted to show it was greater than, which is the norm of u minus p of u squared. Taking square roots of everything in here gets me exactly what I would like to be. Essentially, this says that this u minus p of u is the shortest possible line segment connecting any vector inside of the subspace that we are spanning by these vectors e1 through en. Shortest possible distance between any of those vectors to the original vector that we started with for the vector u. Basically, what that means is if we take a projection of a vector u and take a look at that, it's the best possible approximation in terms of norms and distances to the original vector. But this projection, P of u, might actually be in a space where we could get a more reasonable solution. Maybe this red space here, in terms of our applications, is the space of all of the solutions that are accessible to us, reasonable to get to. Maybe we can't quite get to the vector u with the resources that we have, but this is the part, the closest possible that we could get to the vector u in our solution set, all of the possible things that we consider as viable. By the way, this is exactly how JPEG compression works, MP4 compression, these same sorts of things. All of these are vectors in terms of zeros and ones. And what we do is we take these vectors of zeros and ones and say, we want to find the vector of zeros and ones that's closest to this vector that you also get to have basically a lot of zeros in. We could call those sparse vectors or sparse data. It's data with a bunch of zeros inside of it so that you don't have to have as many bits and bytes to deal with. You can start compressing data a little bit that way. So if you can compress those vectors and then find a way to basically scale it back to the original version, what happens is you don't have to use as much data in the compressed version as you do in the original photo that you might get. You may have at some point seen the size of what an actual 8x6 photo might look like, and it is humongous because every little pixel inside of that image is its own 0 and 1, it's its own byte. It's its own little color scheme. So what we're doing in JPEG compression or MP4 compression or whatever type of thing we're doing is we're saying, okay, I'm going to try and take many of those and approximate what their values need to be as nicely as I can, given that I only know, let's say, the colors and where they need to be in these little spots. And the way that we do that is we don't just pick and choose whichever colors and which spots in those pictures, get the zeros and ones and get their points approximated. We use a compression format, which is something a lot like least squares. It does get a little bit more complicated than that in many scenarios, but that is kind of a rough and skinny way of looking at how this sort of stuff works. So in computing, huge deal that we have this sort of least squares regression, being able to move forward with it. Just a quick theorem that I do see come up a little bit in some things later on. I don't think that we end up getting to use this very much, but I just want to go ahead and show this theorem, which is known as Bessel's inequality, which essentially says that if you take the sum of the absolute values of x with any elements inside of an orthonormal sequence, then you're always going to get something that is less than or equal to the norm of that vector x squared. And this is something that comes immediately from the previous theorem, which says that you can take the projection of the vector p onto the orthonormal sequence that you have right over here, the sequence of 1 to infinity of this vector x. And we know that you can break apart this into two orthonormal vectors, use the Pythagorean theorem. This is Pythagorean right here. You can break it up into two different squares, and that's going to be greater than or equal to this value. And what was this value? We said it was the projection, which we know to be the sum over, for all alpha, the values of the vector x that we're projecting onto the vectors un times un. If I go through and I take that length, then that length by that Pythagorean again is going to be equal to the sum of the absolute values of the x of u sub n quantity squared. By the way, that's exactly what this last component is going to say. I've kind of gotten ahead of myself a little bit with this proof, but that's the essential idea behind this last part of the theorem, is to say that you can then just break this apart, the norm of the vector p of u. This is right here just using the definition of the vector p of u. This one is using Pythagoras. And this one is using the fact that you are looking at a sequence E1 to En of orthonormal set of vectors. So this is true for all possible values that you can get. And putting that formula back in there for the inequality we had on the previous slide, that gives us this greater than or equal to. So we are good to go. Not spending too much time on this one because I don't foresee us using it all that much. But that is a pretty neat way to see that you can be taking projections. And what's more, the projection value that you get here is going to be of length less than or equal to the original length of the vector x that you had. That could be useful in some circumstances if you pay by the meter of what your vector is when you want to project it onto something. Well, one last example to go through before we finish up. So let me get this one prepped real quick. And this one I will spend a little bit of time on, because what I want us to do is not necessarily know all of the theorems and stuff that can be utilized for projections. I don't really see us using Bessel's inequality in particular, although I do see us using projections a good bit. And that's something that I want us to be familiar with. So why don't we take a look here at projections and how we use this formula? It may look obvious from the picture, but the projection of a projection doesn't really do much. The second projection, that is. You take a vector and you take its projection, and then you take its projection onto the same space, then what you get is the same thing that you had from before. Let's go through and see that. Let's see that if you take the projection of a vector v onto an orthonormal set of e sub n, e sub 1 through e sub n, and what you end up getting from that is just the exact same vector that you had from before. Let's recall our formula here, that the projection of the vector p, which we're summarizing here, is the projection onto this orthonormal set e1 through en, of the vector v is equal to the sum as I goes from 1 to n of the inner product of these vectors v with the vectors e sub I times the vector e sub I. So this is, again, the way I'm thinking of this, and the way I know this formula is that I'm thinking of this as just a sum of vector projections. And if I know what the formula is for a vector projection, then I'm good to go, because this is that form of those added all together. So there is my projection of the vector v. So what I want to do is then get a formula for the projection of P of V. So why don't I see if I can try and find out what that is? The projection of P of V will be equal to, I'm going to be utilizing this very same formula, but now I'm no longer taking the projection of the vector V, I'm taking the projection of P of V. So what this is going to get plugged in for the formula that I would have instead of V. So first thing I'll do is just go through and write out the basis of the formula, but I'm going to skip over the vector V. Then I'm going to take what I know I'm replacing vector V with, and I'm going to put in what this is instead. You might notice me use a different letter here. And the reason I'm using a different letter is that I don't know if the i's and the j's ever line up at any point. You see me do this a lot with series. If I'm introducing a new series, then I want to use different indices for the vectors that I get outside of that. But this just being a finite sum, I'm going to utilize the same sort of notation. So let's talk a little bit about what we can do with this problem. Let's get kind of used to some of the principles that we might use here to figure out what to do with these projections. Well, first, let's talk a little bit about how inner products could be useful. We have here a sum of vectors, e sub j, each of which have a scalar, like the inner product of v with e sub j, being multiplied over here on the inside. So what could I do with that? I could take that value right here, the sum of these inner products, And I can use the linearity of the inner product and bring the sum outside. I can also bring the inner products outside. Let's see what that's going to give me. So this is by using linearity of the inner product that I can take the sum outside. Here's the j goes from 1 to n. And I can also bring out the scalars. Notice inner products, they're just scalars. They're just values that I get to take out for free because the inner product allows me to do so. The only thing that's left on this first argument, once I take out the sum and the scalars, is just the vector e sub j. So there's that vector right there. Then I'm going to be taking that inner product of that with the vector e sub I. And also I still have the vector e sub I left over here. Now, let's take a look at these inner products. The inner product of e sub j and e sub I. Looking at these inner products here, I remember that I'm looking at an orthonormal set. So these values are already given to me. This is equal to 0 if I is not equal to j, and it's equal to 1 if these are actually the same vector. The only way that this could be non-zero is if I'm looking at exactly the same vector, in which case I'm taking its length squared, and I know its length is 1. So that's actually going to simplify a good bit here with my formula. The only way that I could get something non-zero in this sum of sums is if I and j are actually the same thing. So I need to be doing this where this is the sum as I equals j, where, of course, either of these values go from 1 to n. So I'll start by doing that. And since I'm only looking at the places where I is equal to j, I know that this is replaced by 1. So here is the inner product of v and e of j times the vector e sub I. Finally, I know I is equal to j inside of this sum, so I can actually get rid of one index. I can just write this as the sum as I goes from 1 to n of the inner product of v e sub I, comma, e sub I. By the way, this formula right here looks very similar to the formula right up here. And it's because they're exactly the same. This was our formula for P of V. So what did we just show? Looking at our inequality here, or our equality here, we started with P of V, and we ended with P of V, which is exactly what we wanted to show. All right, so that tells us about all of the powerful things we can be doing with inner product spaces. We can define angles, find orthogonal and orthonormal sets, and then use those orthonormal sets to define projections. Notice that this isn't that much stuff in the text, but I spend a lot of time talking about it here. And it's that because of this that I find so much importance in the material that's being discussed here. If we're looking for applications, this is it. We're at the cusp now of seeing what applications can be used from all of the theorems and materials that we've been looking at so far. Inner products are one of the big spaces that allow us to do that. So we've talked a lot about these different parts, and I want you to take some time and process this. We'll be practicing these a little bit in our homework, namely looking at main things here, especially thinking of towards the fact that we have our final exam coming in about 2 weeks. I am looking at big things being showing something is an inner product, and then using the fact that inner products can generate norms. Then also showing orthogonality using theorems like Pythagorean theorem and all the things we can do with a Pythagorean theorem, like using it to show orthogonal and orthonormal projections and how they exist. And then also finally, how orthogonal projections behave. Namely, projections give you something that is orthogonal to all elements in the span of the vectors you're projecting onto. And it's also the closest element to the original vector that you might get. But that'll do it for me today. Thank you so much. Have a wonderful day.